An exponential or anti-logarithm converter amplifier is shown here, designed using two op-amps and two bipolar junction transistor BJT. We want to show that the output voltage in this circuit here is related exponentially or in an anti-logarithmic fashion to input voltage that you can see appears as the exponent of the exponential with a scalar that is defined by the value of resistors. How is this possible? And it's an interesting circuit because then it enables us to compute the EXP of, let's say, a given voltage at the input of the circuit. Okay, so let's make the assumption that op-amps are properly biased with the proper supply voltages so that they are operating in linear region for both op-amp. And at the same time, of course, we need to be careful about selection of value of these two resistors, R1, R2 especially. Okay, so with that in mind, obviously the voltage at the positive input terminal of op-amp 1 is computed as R2 over R1 plus R2, a simple voltage divider, times Vn. Since we are making the assumption that op-amp 1 is in linear region with the proper negative feedback here, virtual short is valid. As a result of virtual short, we are indicating or saying that since the virtual short is valid for op-amp, then voltage at non-inverting input terminal or positive terminal should be equal to the voltage at the inverting or negative terminal. So this voltage we found for V of positive should be also the V of negative for op-amp number 1. It appears basically here as well at this node. Okay, so what is the benefit of that? Well, from that node, you can see that we have a plus minus VBE across this transistor T1 VBE from base emitter. So B indicate base here, and then E indicates emitter here. So VBE, we go from the voltage at negative terminal by VBE down to this output of op-amp 1. So what I can say is voltage at the output of op-amp 1 is equal to voltage at negative terminal of op-amp 1 minus a VBE drop for transistor T1. Okay, substituting from equation, say 1 here, so I'm going to substitute for V negative, which is effectively R2 over R1 plus R2 times Vn. Okay, and what do we have here? So this is V out 1, and at the same time we know that we can see because of transistor T2, assuming circuit is operating properly so that both transistor T1 and T2 are active, then we are actually increasing from VO1 by a plus minus VBE2 to get to the base of transistor T2, or basically the negative input terminal of op-amp 2, which is also operating in linear region of operation. So virtual short should be valid for op-amp 2, meaning that since it is AC grounded or it is grounded at the positive terminal because of virtual short, we also get a virtual ground at the negative terminal as well. So we can see that from VO1 by VBE2 we get to 0. So basically this VO1 should be equal to 0 minus VBE of transistor number 2 as well. Okay, so that's interesting. I forgot to also write the base emitter of transistor here was dropped, so I'm gonna make the correction. So there you go. This part should be, this portion should be here as well. So here as well with a negative sign, as was the case. So what I said effectively, voltage at the common node, which is VO1 at the emitter of both transistor T1, T2, can be written in two ways. One way it can be written this way, looking at op-amp 1 and transistor 1, and another way it can be written this way, looking at op-amp 2 and transistor 2. Okay, so effectively we end up with this important equality, and that is basically saying that, so I'm just going to continue writing. So from there I get effectively VBE2 minus VBE1 equal to R2 over R1 plus R2 times Vn, negative sign. What I did, I moved this component to the right side and I moved this component to the left side. That's the only thing I did. Okay, now let's use the base emitter voltage and current of transistor equation. That is basically voltage of, that's the diodic equation. So voltage of base emitter for transistor, bipolar junction transistor, is equal to eta, which is the ideality factor, times the thermal voltage Vt, natural logarithm, the current through the transistor, let's say the collector current, divided by saturation current of the transistor. This eta for BJT is around 2, but in general is a number between 1 and 2. We don't care again because it's gonna, so we're gonna make the assumption that in this example it is 1, for example, but generally speaking for BJT transistor it's said to be closer to 2. Vt, or threshold, or sorry, the thermal voltage is just kT over Q, in which K is the Boltzmann constant and Q is the electron charge and T is the junction temperature for transistor in Kelvin. In this example, let's just use as they are, and then I'm gonna mention another assumption that we are making to simplify the problem. So I'm gonna substitute from equation, say 3 here, by substituting VBE2 and VBE1. So I get eta Vt, natural logarithm. So it would be the collector current for transistor T2, which is effectively assuming that beta for both transistors, which is a practical assumption, is much larger than 1, then we can just say that the current through R3 or I3, let's say, is basically the current of transistor T2. So I'm going to just do I3 over IS. So that's a substitution for VBE2. And then minus eta Vt, natural logarithm. For VBE1, same thing. Beta is much larger than 1. We're going to make the assumption that the current that is coming this way, which is effectively IR, because no current can flow through the terminal of op-amp. Therefore, this bias current or fixed current that is applied, and of course it's our choice, it can only go upward this way toward transistor. So it will be IR divided by IS, and of course on the left side, on the right side, we have the negative R2 over R1 plus R2 times Vn. Okay, so let's simplify. Actually, I can keep eta for now, but later on we can make the assumption it is 1 because it's a constant, it doesn't matter. What I need to make sure we are on the same page about is we make the assumption that these transistors T1 and T2 are actually on the same substrate and they have similar properties. So they have similar junction properties, similar thermal properties. Reason for that is, therefore I can factor out eta Vt for both ln or natural logarithm here, assuming they are equal. So with that assumption, which is a reasonable assumption, both transistors on the same substrate, copy paste of each other. So we get eta Vt equal times natural logarithm I3 Is minus ln IR Is, which effectively just become natural logarithm of I3 over IR, and the nice thing is IS cancels out and we get rid of that saturation current that is heavily function of temperature, so we get rid of that level of temperature dependency, equal to negative R2 over R1 plus R2 times Vn. We are done, because the next action is I'm going to just take a exp of both sides, and I get exactly as we wanted to get. So what I'm going to get is almost there, because then next action after that would be I am going to also replace I3 easily. So for now, I3 becomes equal to IR, and then we have exp, or e to the power of course, negative R2 over R1 plus R2 times Vn divided by eta Vt. Okay, so the last action I need to do, so this is equation, say, 4, and the last action I need to do to complete the problem is find the I3. If you look at I3 in the circuit, if I change the color so that you can see what I'm talking about, I3 is the current going through the resistor R3, and you can see that because of virtual short, we have virtual ground on negative terminal, which means this side of resistor, or the left hand side of resistor R3, is 0 volt, and the right hand side, of course, is V out. Therefore, current I3 can be easily computed, saying I3 is equal to just with the direction that I'm showing is just V out minus 0 divided by R3. So I'm going to just substitute that. This is equation 5, and just using 4 and 5, so using equation 4 and 5, I can also write it here, but it doesn't matter. So basically I'm going to just substitute for I3 V3 over R, and then move R to the other side, and I get the result. So V out is equal to, therefore, as I said, substituting I3 with V out over R3, and then moving R3 to the other side, I get R3 times IR, then exp of, or e to the power, and exactly what we wanted to get, negative R2 over R1 plus R2, and then times Vn over eta Vt, in which, if we make the assumption that eta is actually closer to 1, then we get the result that is indicated in this problem. So we managed to show that this circuit really implements sort of an exponential or antilogarithm calculator. So there are two names for this circuit, as you can see in the title of the circuit. One name is exponential converter or amplifier. The other one is antilogarithm converter amplifier. So we managed to implement that, but we need to be careful about the selection of value of resistors. R2, generally speaking, in this kind of simple circuit, R2 is selected to be considerably smaller than R1, so that we manage the amount of additional voltage we are adding to VBE, because VBE of transistor has a limited wiggle room. So I hope that this example is helpful.